We had been looking at the ideal opamp model, but let us look at a practical opamp model now. The ideal opamp model stated that there does not flow any current from the input terminals to inside of the opamp. These currents are zero, no current flows in here, and that the voltage between these two terminals, let us call this V in, is zero. This is the ideal op-amp model. Whereas that is an idealistic simplification of how op-amps work. But let us come up with a practical op-amp model that is not that simple, but it represents some better approximations of what happens inside an op-amp. So, for example, look at this model. In this model, there are two terminals going into the op-amp. So let us assume that there is a resistor between these two, and then there is a resistor at the output terminal, and here we have a voltage controlled voltage source. This is a voltage source, and it is being controlled by this voltage, the input voltage. This is the inverting non-inverting pin, and this is the inverting pin. And let us say this voltage is Vd, the difference voltage, the difference between these two. And this resistor is what is known as Ri, because we are looking into at the inside of the op-amp. This is the input resistance, and this is the output resistance that is related to the output pin. And this voltage controlled voltage source is represented by a parameter known as A into Vd. So this Vd controls what voltage will be here, and it is A times Vd. So there are three very important parameters that are there in a practical op-amp model. A is known as the open loop voltage gain. Ri is known as the input resistance, and Ro is known as the output resistance. The open loop voltage gain is when there is no path from the output to the input. Usually there is a path, as I have mentioned earlier, that all the op-amp configurations that we will use, there will be a path, a resistor, or maybe a direct wire or some other thing from the output terminal to the inverting input, and this is known as negative feedback. We will come to that later on, why it is a negative feedback. But if there is nothing from the output pin to the input, then the output, then the open this voltage, when there is nothing connected here, the ratio of this voltage VO and this voltage VD is what A is, and it is usually very high. It's usually very high. In practical op-amps, this is like 10 raised to the power 5 to 10 raised to the power 6, maybe. So it is like 100 kilo to 1 million. It's a big value. It's the gain of the amplifier when there is nothing, there is no feedback loop, and the input, whatever this voltage is, gets amplified by this amount A, and this is how the VO depends on the input. The input resistance is typically very high too, like in from 1 mega ohm to say 1 or more 10 tera ohm, a very large value, very large input resistance. This is what these are the values and the practical values that there are for op amps that are being constructed. And the output resistance is a small one, usually maybe like 1 ohm to 100 ohm in practical op amps. There is a very popular op amp known as a UA741. For example, this A for this model of op amp is 2 into 10 raised to power 5, that is 200,000. The input resistance is like 2 mega ohm, that is 2 into 10 raised to power 6 ohms. And the output resistance, as mentioned by the manufacturer, is 75 ohms. So this is actually a practical model. We are no longer saying that there is no current going inside, but we are trying to model the pins. In the ideal op amp, we can model it like there is nothing connected here. That is why there is no flow of current to the inside. But in reality, there must be some, the internal circuitry must be presenting some resistance, although it's very high, but there is some resistance. And the construction of the op amp is such that the output resistance is tried to be minimized as much as possible. And there are op amps, for example, where this resistance is up, say 10 tera ohm, and there are op amps with 1 ohm of output resistance. So this is a practical op amp model now. So in a typical inverting configuration, we have already used the ideal op amp model in trying to solve this case. So we have Vi here, Ri here, and Rf here, and we have found that VO is equal to negative of Rf over Ri into Vi. This is how, using the ideal op amp characteristics, we can we can find the relation between VO and Vi. Now, where is this Ri in here? We see that the output voltage does not depend on Ri. Output voltage does not depend on RO. The output voltage does not depend on A. So where are those mysterious figures, mysterious values? If VO does not depend on those, what is the use of having them at all? In fact, if you look closely, in an ideal op amp, A is considered to be very, very large, infinite value. Ri is also very large, infinity, and RO tends to 0. This is an ideal op amp model where these parameters are considered to be these. In reality, they are not so. A is a large value, Ri is a large value, RO is a small value, but they are still finite and there. So let us consider the same circuit and use this ideal op amp model to make it. So we have this VO here, and we know there is a resistor from VO to the inverting input. Yeah, this is the inverting input, this is the non-inverting input, and this voltage is VD here. This is Ri, this is A VD, and we have here we have a resistor Ri and a voltage source connected here, Vi, this one. And the RF is connected between the RVO and this inverting input. So let us try to solve this. And what have we done of this? It's obviously it's grounded. So let us solve this circuit, and let us use all the circuit solution techniques that we know. So let us use our knowledge of circuit solution techniques and find VO in terms of Vi, just like this. And let us try to find for this. So if this is ground, we can see that this voltage would be minus Vd, because this is 0 and this must be VD. This is the higher potential, so the lower potential must be minus VD. And this is obviously VO. Let us write the NVA equation for this node. So minus VD minus VI over RI plus minus VD minus 0 over Ri. Oh, let us, this Ra is different, this Ra is different. Let us consider this to be Rn. Ri plus minus Vd minus Vo over Rf. So how many branches here? 1, 2, 3. We have three terms is equal to 0. So we know what is uh, Vi, we know what is Rf, we know what is Ro, and all these things. Vo is not known, so we want to find Vo, but we have this Vd here as well, so we need another equation. Let us write that equation here. We get Vo minus AVD over Ro plus Vo minus minus Vd over Rf equal to 0. If we solve this offline, I have solved this offline, and we can come up with the equation of VO to be equal to RO plus RF over RO minus A RF 1 over R1 Rn actually plus 1 over Rf plus 1 over Ri minus 1 over Rf whole inverse into Vi over Rn. Don't spend time in trying to prove that you can ultimately get this. Just believe it. We can solve these two equations. For example, we can find the expression for Vd from here and put it in here. We can obviously simplify them to ultimately find what is Vo equal to. We will get something like this. So suppose if we have this Rn to be equal to 4.7 kilo ohm resistor, this Rf to be 47 kilo ohm resistor, and this Vi is a 5-volt source, then using the ideal op-amp characteristic, we can find Vo to be equal to minus 47 over 4.7 into 5, that is minus 10 into 5 or minus 50 volts. Here the gain is negative 10. But if we take the typical values, for example, for the 741 op-amp, where Ro is equal to 75 ohms, Ri is equal to 2 into 10 raised to power 6 ohms to mega ohms, and A is 2 into 10 raised to power 5, then we can solve this and see that Vo ultimately comes out to be equal to negative 9.999448 into 5. So just look at the gain here of minus 10 and the gain here. So you can see that the ideal op-amp model is quite a good approximation of an opamp, even practical opamp circuits, and we don't actually need this complicated model to solve the ideal op-amp characteristics. Let me also emphasize that an actual op-amp from the inside is not like this. It's a very complicated circuit, a lot of transistors used, and we cannot discuss this in this course. It's beyond the scope. And this is an equivalent model as well. It's a practical model. This is an ideal model. But we have just seen that an ideal op-amp model is a good approximation of an op-amp. So all the circuits that we will solve, we will be considering the ideal op-amp model. And in a later video, we are going to look at why do we use this feedback, what is the purpose of this, and what is the purpose of having a large, for example, open loop voltage gain. And consider this, the large open loop voltage gain to be so big, but the actual circuit that we have here in inverting configuration has a gain of only 10. So how do these two compare? Why do we have a very large open loop gain and a small closed loop gain? So this is known as a closed loop gain, voltage gain. So what's the difference between a open loop voltage gain and a closed loop voltage gain? When there is no feedback, it's open in open loop. When there is a feedback, it's in closed loop. And just look at the values of the two. One is very small and the other one is very large. In a later video, we are going to look at some of these considerations and discuss them. Even mathematically, if we put in this equation, if we put Ri, the input resistance, to be infinity mathematically, and Ro, the output resistance, to be 0, and the open loop gain to be infinity, if we just put here, for example, 1 over Ri is going to become 0, this Ro would become 0, so Ro plus Rf would become Rf, and A into Rf would become infinity. So something over infinity is going to be 0. So this whole term will become 0. And what are we left with? This 1 over Rf becomes, because of this inverse, comes to the in the denominator. So we are ultimately left with the same expression, this one. So mathematically, if we apply the ideal op-amp characteristics to this practical op-amp model based expression, we are going to get the same expression, VO equal to minus RF over Rn actually, because we have changed it into VI.